Hello, good afternoon, everybody. Welcome to the next audio showcase at Plaza 2024. Very pleased to say that this afternoon we've got insight into the latest spatial audio techniques at one of the biggest festivals in Europe. As I say, EDM festivals, Tomorrowland in Belgium. And we're going to find out all about how the audio this year has taken a quantum leap forward, shall we say, and how those solutions were arrived at. So without further ado, please meet Mr. Jack Human, who is the Senior Project Engineer at Holoplot. Holoplot makes the X1 array, completely new kind of loudspeaker, and Jack is a graduate of Solent University, a freelance sound engineer, and worked with a more local company called Aerial, based in Antwerp in Belgium, who were originally part of the Tomorrowland setup, have now established their own independent company developing software for spatial audio. So, ladies and gentlemen, Mr. Jack Human, thank you.
Hello, everyone. There we go. So we'll start with a quick introduction to Holoplot and what we do. So we pride ourselves on three key mission statements, and they are sound control, sound intelligence, and then that leads to sound quality. So we start with sound control. We do this through 3D audio beamforming, so a new technique that's enabled by our matrix array X1. This enables us to control sound in both the horizontal and vertical axis, which leads to greater listening experiences. We also use wavefield synthesis as well to create virtual sources within 3D space. Sound intelligence, the next statement of our mission, is done through our software suite, but also our smart systems. All of our loudspeakers are connected through the Internet of Things and also connected to the Internet, and this allows us to access our systems anywhere in the world, do remote monitoring, and also push over-the-air updates to the system. So not only is your system improving over time as our algorithms and innovation continues throughout the company, and ultimately, this leads to sound quality. So we're controlling that sound, and this was an issue at Tomorrowland, which we'll get into in a bit more detail as we go through. We're controlling that sound, minimizing reflections, and therefore improving the listening experience. So how have we innovated through? We have a little bit of a history lesson. We started out with the point source, radiating omnidirectionally in all directions. And then this developed into the line array, which gave us control in the vertical axis. With the matrix array, the next development, this allows us to control the sound in both the horizontal and vertical axis. And we can also define our listening areas in 3D space as well. So they can be any shape, and we can also have multiple of these listening areas, which we used at Tomorrowland. And again, when we get into the project, we'll talk a little bit about that in a bit more detail. So our powerful optimization algorithms, we can define the coverage area, and we can also define areas we want to minimize the sound as well, and we call these avoidance areas. This results in an improved sound field homogeneity, making sure that every seat or every listening position is equal. And then each of these individual beams, so you see in that example, we've got multiple beams, each is individually processed through its own DSP, so EQ, time alignment, everything is individual. So a way I like to sort of describe this is ignore the array and think of the beams as individual sound sources, because each of them may be coming from one location in a single array, but can have its own unique content. For example, we can have half the audience in English and half the audience in German from a single array. So what's the hardware that enables us to do this? This is our X1 range, our big loudspeaker that's in the Sphere and also in Lightroom in London, and was also used at Tomorrowland. And that consists of two variants. We have the MD96 and the MD80S. And if we look at the MD96, this is a two-way loudspeaker module, which consists of 96 drivers. Each of these drivers is individually amplified and processed. So we've got 96 channels of amplification, all in the active box itself. And that sits within two layers. So we have 78 1.3-inch soft dome tweeters that sit in the front layer, and then behind that we have 18 5-inch cone drivers. And each of the cone drivers is in an individual dual ported chamber, and the tweeters, all 78 of them, have their own waveguides also. And then the second module we have is the MD-ATS. Now this is a 3-way loudspeaker, and we have 80 drivers, so we lose a few of the drivers for the port cutouts in the corners. We have 16 1.3-inch soft dome tweeters, coupled with individual waveguides, and again 16 5-inch cone drivers, individually ported chambers also. And on top of that, in the rear, we have a single 18-inch iPower sensor-controlled subwoofer, which is within a bandpass enclosure with airflow optimized ports, which is why we have 80 drivers compared to the 96, because we lose some of that space for the ports in the two corners with the MD-ATS. So, what did we do at Tomorrowland with Holoplot? So, Holoplot worked with Ariel to develop the system within the which stage was it? Sorry, Atmosphere stage. That's the one. So within the Atmosphere stage, we wanted to create an immersive listening experience and also enable upmix from stereo content to multi-channel. And we worked with Ariel on this to create the ultimate electronic music immersive experience. So here's a view of the outdoor stage. So you can see a very large tent, and then also you can see the bit that extends out the back there. That's a chill out area as well. So again, our sound control enabled us to keep that area quiet and enabled us to minimize the spill outside of the tent. So let me briefly introduce the festival. The goal was ultimately to create the quality immersive sound experience while minimizing reflections. So we've got a huge canvas tent above this. We've got sound reflecting back on it, and these late reflections are muddying the sound, and therefore our 3D audio beamforming technology enabled us to minimize those reflections. We wanted to create a small club feeling within the large tent also. So it's 3,500 capacity within this tent, but we wanted to create the ultimate sort of small experience for everyone. The sound should complement the ultimate immersive experience within the wraparound LED within the tent, and also the visuals and lighting that's used there. So the tent is 35 meters tall, 20 meters wide, and as I said, has a capacity of 3,500. And these reflective surfaces were causing a real issue in past years, and that was why we were approached to solve this issue. And then the content was also stereo, but as I said, we worked with Ariel, and this was then in real time upmixed to our multi-channel system outputs. And here's another visual inside, so you can sort of see that wraparound LED and how immersive that feeling is within the tent. So what was our solution within the system design? Here's a visual of the system. We had two main layers within the system. This consisted of the frontal system as well as the surrounds. So the frontal system, we had a left and right 3x2 X1 mixed array. So that consists of both the MD-ATS and the MD-96 modules. It was 4 MD-ATS and then 2 MD-96 per side. And then we also had additional third-party subwoofers for additional low-frequency reinforcement. And then we had 6 surrounds that you can see positioned around the listening area there as well. Each of these was a 1x2 matrix array, and they consisted of just 2 MD-96 modules. So in total, we had 16 X1 MD-96 and 8 X1 MD-ATS within the tent. So the issue we face with large immersive deployments is always within the time domain. We can only time align systems to one point in space. So if you can imagine, we're at the front, and then we're getting the frontal system and then the rear surrounds. Because of that time of arrival and the distances that sound needs to cover, it's impossible to time align that for everyone. Usually we pick the middle point, and that creates a small area that is then sort of the immersive sweet spot. So we were like, well, how can we improve on this? How can we use our technology, our capabilities to improve this and really open up this area to give more people the immersive experience and open up that sweet area? So with Holoplot, as I mentioned at the start, we can also have multiple output beams. So we can have up to 5 coverage beams per array. And in this case, we had the frontal arrays. Each of those had a single coverage beam that was optimized to cover the full audience area. So that's the frontal system. And then we were like, So the issue will be if you're stood at the front and these rear surrounds are hitting you, and then that time alignment, like I said, and you've got those perceived echoes and you're hearing two auditory events. So we were like, well, let's take the middle surrounds and create two beams from them. As you can see in the visual here, we have a beam that's covering the front half of the audience area and then a beam that's covering the rear half. So if you're stood in that, what we call the immersive area, the circle in the center, and you're stood at the front, one of those beams from those sides, the mid surrounds, is optimized to be your rear surround. And then the other beam, if you're towards the back, will be your front surround. Therefore, each of those, as I said at the start, we can have individual time alignment on. So we're solving that issue of the time domain, and we're really opening that suite area and allowing more people to be in that immersive sweet spot and not cramming everyone into a center point where it's then like the true immersive feeling. But also, as I mentioned, that's a huge reflective canvas tent. And these slapback echoes that you're getting from that tent was a real issue in the past. So we were able to minimize the energy onto the tent as well. So if I go back in this visual, you can actually see where we modeled the actual tent, and we can use something that we call avoidance zones. So while I'm optimizing a beam, I can choose the areas I want to cover. So in this example, I'll say that green area, I want the frontal arrays to cover all of that. But then I can also select avoidance zones. So we said, okay, so we want to minimize the energy on that tent. So we selected the entire tent to be avoided. And that allows us to really control that sound away from it. But also, we can all do that with line array in the vertical axis, but with the matrix array and X1, we can do that in both axes. So we were able to keep it off the side walls as well. So really, you're having your frontal system, and then you've got frontal surround and rear surrounds. And it depends where you are to which of those is your frontal or rear. Hence the two beams from the mid surrounds that you see there. So the front surrounds will be optimized to only cover the front half of the audience area. Then we've got those two beams that you can see change in between. And then the rear surrounds are optimized to just cover the rear half of the audience area. So what benefits did this give to us and also the Atmosphere stage at Tomorrowland? It allowed each half of the audience area to be time aligned to the frontal system correctly. So we're really reducing those perceived echoes, and we're not hearing two auditory events, which is very jarring, especially within EDM music, where it's very transient as well. And then you've got, say, like a snare hit, hi-hat hit, something like that, that's then just coming at you twice from two different directions out of time. So we were able to solve that issue. We were then able to create a much larger immersive area, as I said before, and then also reducing those reflections. But then another key point, as I said, when I showed the tent, we had that chill out area right at right next to our tent. And we were like, well, we don't want to be blasting people chilling out in that area with sound. So we were able to also create avoidance zones outside the tent, therefore minimizing the noise pollution outside of the stage. So let's talk a little bit about Aerial and the upmixing that we had at Tomorrowland with this. So Aerial it came out of Tomorrowland, a Belgian company, as was introduced at the start, and it allows for real-time upmixing from stereo to multi-channel output. So the upmixing can be up to 8 channels with a single core, but we can have up to 3 additional cores as well. So we can have all of those 4 cores, each with the 8 channels. The whole algorithm has a latency of less than 6 milliseconds. We're not using any additional harmonics, reverb, delay, or phase shifting applied to the signal also. And it's only taking from 500 hertz up and then up mixing those frequencies as well. It's also fully 3D capable, so we can have height layers in there. We can work with Dolby Atmos, things like that. Any format is fully customizable within the software. We just need to know where our output channels are in relation to where our loudspeaker positions are. Inputs and outputs can be analog, AES, Dante, or AVB also. And the upmix signals can be combined with traditional stereo delays, infills, outfills, etc. So we've got full freedom of the system there. So the low latency warping algorithm allows users to control and steer low frequencies of all sound sources without affecting the upper frequencies also. So it was really interesting to work with Ariel. We did a demo in Germany, actually. So we're a German company, Holoplot. We did a demo with them in Germany. And from that, this is how the whole project at Tomorrowland came about. Really, like I said, very, very interesting to work with them and how we can combine our technologies together to create the ultimate immersive listening experiences, especially with EDM and at Tomorrowland. Oh, I've lost my notes here. It was a very quick and short presentation, but has anyone got any questions about what we did at Tomorrowland? I'm happy to have a chat.
Yeah, I'm interested how you're doing. Oh, hello.
Have we got a microphone?
I can talk loud. Don't worry.
I'll just take my headphones off.
Yeah, you'll be fine. If the Dolby Atmos. Yes. Thank you very much. Thank you. Saves my voice. Oh, much sexier. Your use of Dolby Atmos, which decoder are you using, or is there one built into the Ariel device?
So I believe there's one built into the Ariel. We weren't using Atmos at Tomorrowland.
Okay.
We were just using multi-channel output. So we were taking the stereo content, and then the engine is just taking that out to our side surrounds.
Okay. I'd be interested to see how you progress. I've been lucky enough to work with Atmos for 11 years now. I think it's brilliant what you're doing. I think you're going to have a lot more fun with this. Thank you.
Yeah, I mean, the system, Holoplot's totally flexible. Like I said, the key thing is to not think about the arrays, but think of the beams. So like I said, we can have up to 5 different beams targeting different areas as well. So the possibilities are limitless as well. And we're open. We work with any format. We can take a Ravenna or a Dante channel. So each of those beams is just a Dante or Ravenna channel.
Yeah. Now we're looking at your stuff for a project in Amsterdam right now, and it's you walk into the beam, you walk out. It's an augmented gift.
Yeah. And I think within festivals is a really interesting segment for us now, because since COVID, restrictions on festivals have become a lot tighter. So local residents got used to the quietness. Festivals came back. Noise restrictions got a lot tougher. So that's key for us. We want to maintain those listening experiences for the audience without the annoyance of neighbors and things like that, and maintain these festivals, otherwise they're going to get closed down. But another thing is also, when you're thinking about how you lay out a festival, you need to really consider that, because you need to minimize the crosstalk between stages. With the control that we have a lot more flexibility to even put more stages within a smaller area.
And your steering of subs, so how are you doing that with time delays or?
So everyone always thinks that controlling low frequencies is the hardest. Controlling low frequencies is easy. You just need an array big enough to do it. You need an array that matches the wavelength that you need to steer. Otherwise, it's just physics. If you haven't got an array big enough to control that wavelength, then you can't control it. It's always the high frequencies that are harder, because that depends on your driver spacing within the hardware.
Yeah, lobes.
And that's fixed, which again, if I jump back to, you can see the randomization of our driver layout. And this is to minimize lobing. So creating lobe with any steering sound is always going to be an issue. But within our optimization algorithms as well, you can see those lobes. And it's about driving that frequency as high as you can within your driver placement, your driver layout, so it's less of an issue.
Okay. Cool. Very grown up. Thank you.
No worries. Anyone else?
Thank you very much for your presentation. It's very concise, very detailed. I mean, given the advantage of Holoplot having tight control in terms of the sound pressure level distribution, there's a no-brainer for productions that demands noise control, like open air outdoor parks or Tokyo Dome or neighborhood that is very sensitive to noise. But then the other factor is like the cost to SPL, but particularly in Tomorrowland, it's EDM that demands a lot of sound pressure to entertain it. So how would you sort of take on this factor? Is there any like a reference or guidance in terms of this aspect?
So we were actually achieving 105 dBA at front of house, and front of house was I've gone the wrong way. Front of house was right at the back. So right at the back, we're achieving 105, and we're about 107 in the center of the audience area. So in terms of SPL, we're achieving very, very good SPL, and that's dBA. But you are right. When we're controlling that sound, there is a limitation in the SPL, because we want to create the same level across the whole audience area. So our algorithm will look and it'll know, right, we're going to be achieving, say, 100 dB at the rear of the audience area. So it will reduce the level everywhere else to match that. So we're creating the same level across the audience area. But the other thing is, with Holoplot, you don't need to be as loud as you expect. So we have a festival in Spain, and we typically ask the front of house engineers, we cover the SPL meter, and we'd say to them, what do you think you're mixing at? And they'd be like, 103, 105, and they're mixing it like 96, 97. Because of the control, it's so present and it's so in your face, and it's just that direct sound, you actually don't need the level. So it's less fatiguing on hearing also. Does that answer your question?
Yeah, so you mean you achieve the perceivable or audible level without actually getting to a higher sound pressure level on the meter, right?
Yeah.
So that sort of offsets the cost that is required to as compared to using a conventional liner.
Yeah. And also another key thing is when we do our demos, and then I'll pre-warn people that say it's about to get louder, we do some stereo listening, people step back away from the system because they expect that if you're close to the system, it's going to be loud, and as you move back, it's going to get quieter. But with Holoplot, it maintains that level across the audience area. So people step back and then they walk forward and they're like, actually, we're getting the same level no matter where we're walking. But we can change this as well within our algorithms. We have control of manipulating the drop per doubling of distance. So when I'm creating an optimized coverage beam, I can say to the array, I want you to be acting like a line array. I want a 3 dB drop per doubling of distance. I can go 6, I can go up to 12. So I can actually choose that. So if you want that application where you want it blaring at the front and a little bit quiet to the rear, we can actually manipulate that and change that within our algorithms also.
Can I have one more question?
Of course.
So I understand, there are other manufacturers who would do like similar strategy, but not using the same kind of philosophy that you apply. And there is always a compromise when you activate avoidance algorithm. So how much does it give an impact in terms of the Holoplot system if you enable or disabling the avoidance side of system focus?
So there's two options when it comes to avoid. We can either avoid areas or we can just ignore them. So the algorithm won't consider that area within it. It will still control the sound within the area you want it, but it will just ignore the other. And then I can also actively avoid, which you're correct, there will be a compromise that you have to settle with there. But we use also what's called relative priority. So within Holoplot Plan, which is our design and simulation software, I'll have, say, my audience area here and one here, and I'll say cover this area, avoid this area. If I put both of those relative priorities to the same, say they're both 0, then it will treat them equally. It will say, okay, it's just as important that I avoid this area as it is to cover this area. Or I can say the relative priority to avoid maybe, so if we could say 0 to 1 scale is 1, so the algorithm goes, okay, so it's more important that I minimize the energy in this area than cover this area. So you might have a drop off as you move towards that area in the coverage. But again, all of this is customizable and changeable within our software.
Thank you.
No worries. Any other questions?
Yes. First, thank you for the presentation. I know all here is outdoor. Can you mention a little bit about indoor, like the Las Vegas, the Sphere, or some of those
Yes.
indoor environment?
Yes. Well, where we really see Holoplot shine is in really, really challenging acoustic environments. So the Sphere is the most challenging acoustic environment. If anyone goes, oh, we're going to build a massive Sphere, let's put a sound system in it, that's an awful idea. Why would you do that? It's just going to focus all the sound down to a point and it's going to bounce around. So the Sphere, able to have that control, keeping it away, maintaining it in the audience areas. Here in London, we have Lightroom, which is a huge, huge concrete box in the basement underneath the Meta offices. And again, we went in there, I clapped, and I was like, yeah, this is going to be a challenge. But we were able to keep that off the side walls, off the rear wall, to minimize that slapback as well. Maintain speech intelligibility for the dialogue throughout the shows.
Okay, thank you.
We also, interestingly, have a mosque. So speaking of like speech intelligibility and control, we have a mosque in Cairo that has X1 installed. Has a mid-frequency reverberation time of 6.5 seconds. And we achieve, across 90% of the audience area, 0.65 STI. So to give you an example of how Holoplot really, really shines in these really difficult environments.
Okay, can I add on a question about the cost? Because I think there's a concern about the cost here. To build the Sphere and the audio system there, I don't know the amount of speakers, but it's a lot.
Yes.
Can you mention a little bit about the configuration and how costly is it compared to a normal line array system?
So it's a premium product, it's costly, but it's active as well. So within that module, you're also getting all the amplification as well. In terms of the Sphere, it's 1,600 X1 modules, and obviously the whole project was approximately $2 billion. See, I can't talk around the financials of the audio side. In terms of a line array, in terms of cost, yes, it's slightly higher in its cost, which is where we see X1 really shine where there's an issue to solve that no one else can solve. But as part of that, you get our full connected service packages. As I mentioned at the start, all of our systems around the world are connected to the internet. If I've got an issue in Korea, I can remote into that system, support their engineers on site and fix issues. And also software updates. You're not just buying a box with some drivers in, you're buying essentially a very powerful computer as well. And our software team is the biggest department in our company. So we always say we're science-based, software-driven, hardware-enabled. So based on theory, all driven by our software, but there was no hardware to do that, so we had to develop the hardware to go with the algorithms that we developed as part of the software. Anyone else? Well, that's that. Thank you very much for coming along. I'll be around if you want to grab me and ask some questions also. Thank you very much.